Hi there, welcome to lecture 10 on power series. We're in section 11.9 of our book, Stuart Calculus. For those of you just tuning in, this is a lecture for my Calc 2 students and it assumes a little bit of background we're not going to go into in this lecture. You're welcome to try to figure it out if you haven't had Calc 2, but my guess is if you have not been sitting in on a Calc 2 course or studying it, or have studied it, you might have a hard time understanding it, but feel free. Anyway, we have been describing functions as power series, and at this stage we've only described functions as power series around the point a equals 0. And I want to just kind of talk about how we would do it around the point a equals some other number that makes sense. So let's look at this first one. This first one here, if you recall, this is one we described first around a equals 0, because that's a straightforward geometric series, right? And as far as geometric series go, that is just simply equal to sum n equals 0 to infinity of x to the n if the absolute value of x is less than 1. However, I want to expand it around a equals 2. So I actually want it to look something like n equals 0 to infinity of some constant times x minus 2 to the n. Some a sub n times x minus 2 to the n, and figure out what interval that's going to work on. So the thing is I want to get this as a constant times x minus 2 in a geometric series form. So what we had before is 1 over r, 1 minus r. We could get it in this form where r is equal to a constant times x. Then we get a geometric series expanded around x equals a equals 0. But now I want to get it as a constant times x minus a. And in this case, a is equal to 2. So what I'm going to do here is just add and subtract 2. So let's go over here, and I'll say this is 1 over 1 minus x. I'm going to do plus 2 minus 2. So I can write that as 1 over, so if I have minus x plus 2 and factor out a minus, that's going to be minus the quantity x minus 2. So I'm going to have minus 1 minus the quantity x minus 2. And that's where I get the x minus 2. Of course, this isn't quite right. I need to factor out a minus here. So it's going to be minus over 1 plus x minus 2. So what is my r going to be in this case? My r is going to be negative the quantity x minus 2, right? So as long as that thing is less than 1, the absolute value of that thing's less than 1, this is going to equal the power series minus 1 to the n, x minus 2 to the n. And of course, when we're dealing with geometric series, we don't have to worry about the endpoints. But what is this domain here? The absolute value of minus x minus 2 less than 1, well, that's the same as x minus 2 less than the absolute value of x minus 2 less than 1, right? So that's minus 1's less than x minus 2 less than 1. The radius of convergence is 1, and if I add 2 to both sides, which is the thing I'm expanding around, I get 1 less than x less than 3. The interval of convergence is from 1 to 3. So the idea is when you're expanding around something besides 0, you want to get everything in terms of x minus 2 rather than just x. Okay, so now let's go back over here. Again, I want to get things in terms of x minus 2 rather than x minus 3 rather than x. Now, let's actually go back to this first one here that we were looking at. This. Notice this is defined for all x not equal to 1. We should be able to expand it around any a except for a equals 1. This thing is defined for all x bigger than negative 1, right? As long as 1 plus x is bigger than 0, this is defined. So we should be able to expand it around any such x. Now, we're going to try this. We're going to write this as ln of 1 plus well, maybe we can actually write it as the derivative first and then rewrite that. So we see this as the c plus the integral of dx over 1 plus x. And let's go to the side and look at 1 over 1 plus x. Now we know how to write that as a power series expanded around 0, right? But let's expand it around 3. So I'm going to write this as 1 over 1 plus x minus 3 plus 3. So the plus 3 I want to bring with the plus x. Well, the minus 3 I want to bring with the plus x. So that's going to be, so 3 and 1, that's 1/4 plus x minus 3, right? I'm going to factor out a 4, so that's going to be 1/4 times 1 over 1 plus 1/4 times x minus 3. And finally, what's my r going to be here? R is going to be the negative of that, so I'm subtracting that. So this is going to be 1/4 times the sum, n equals 0 to infinity, of 1/4 x minus 3, the whole thing raised to the n. And this is as long as this r, which is 1/4 times x minus 3, is less than 1. So let's rewrite this. This is going to be 1/4 times sum, n equals 0 to infinity, of 1 over 4 to the n, x minus 3 to the n, which is n equals 0 to infinity of 1 over 4 to the n plus 1, x minus 3 to the n. And this is, so what is this domain? This is going to be if x minus 3 is less than 4, right? Or -4 is less than x minus 3, less than 4. So the radius of convergence is 4, and then I add 3 to both sides, and I get -1 less than x, less than 7. Okay, so the radius of convergence is 3. So with the radius of convergence 3 around a equals 3, right? Sorry, the radius of convergence was 4. We had a 4 down here. So with the radius of convergence 4 around a equals 4, it's going to be some interval between -1 and 7. We're going to have to deal with the endpoints later. But according to what we did before, this is equal to the integral of the sum, n equals 0 to infinity, of 1 over 4 to the n plus 1, x minus 3 to the n dx. And we can integrate this term by term. That's the big theorem. So this is going to be the integral from, this is going to be c plus. When I integrate this term by term, okay, let's pay attention to what we have here. 1 over 4 to the n plus 1 is constant. I could try a u substitution, u equal x minus 3, but I don't really need to because du is just dx. That's going to be 1 over 4 to the n plus 1 times x minus 3 to the n plus 1 over n plus 1. And there we have it. We can rewrite that if we want to as c plus sum n equals 1 to infinity of 1 over 4 to the n times x minus 3 to the n. Okay, so now I'm going to erase this bottom thing here, and let's just see what's happening at the endpoints. We know this here is equal to that power series with a radius of r equals 4. Let's just see whether the endpoints are included or not. And we'll find exactly when that's equal. So endpoints So we're going from 3 minus 4, which is minus 1, to 3 plus 4, which is 7. So let's say x equals minus 1. That's going to be, oh, what's c? Let's first get c. Well, how do I get c? Let's plug in x equals 0. So at x equals 0 here, so at x equals 0, what's ln of 1 plus x? That's ln of 1, which is equal to 0, right? That's at x equals 0 here. And at x equals, oh, sorry, we don't want x equals 0 because we want everything to cancel. Here, let's do this in a minute. So this here, what cancels most of the terms over there? 3 cancels that. So we're going to plug in x equals 3 to solve for c. So at x equals 3, this side here is going to be ln of 4, right? And this side over here at x equals 3, this side here is going to be c plus 0. All of these other terms cancel. So this side here is just c. So we get ln of 4 is equal to c. So c is equal to ln of 4. And so this power series is equal to ln of 4. That's the constant plus the sum. N equals 1 to infinity of 1 over 4n times n, x minus 3 to the n. And finally, let's just see if it converges at the endpoints of the interval. So at x equals -1, what have we got? Well, that ln of 4 is really not an issue. We're looking at this thing here. Does that thing converge? So n equals 1 to infinity. When I plug in -1, I get -4 to the n, which is -1 to the n, 4 to the n, over 4 to the n, which is sum n equals 1 to infinity of -1 over n to the n over n, which of course converges, right? Because it's an alternating series, terms going to 0. And what's the other endpoint? X equals 7 is the other endpoint. And again, we don't care about this constant ln 4 if we're looking for convergence. We're just going to look at this. N equals 1 to 0, infinity. When I plug in 7 into this, I get 7 minus 3, which is 4 to the n over 4 to the n. So I just get 4 to the n over 4 to the n times n, which is equal to the sum n equals 1 to infinity of 1 over n, which diverges. It's a harmonic series. So let's summarize. In summary, ln of 1 plus x is equal to the constant ln of 4 plus the series n equals 1 to infinity of 1 over 4n n times x minus 3 to the n if, so what is the interval of convergence? Well, it contains -1, but it doesn't contain 7. If x is in the interval from -1 to 7. And that is the power series expansion of ln of 1 plus x if we expand it around a equals 3. Okay, this is a good place to stop. Bye.